Hello everyone, welcome to my fourth video, Introduction to Logic Gates, also known as What Makes Redstone Awesome. Because with Redstone you can implement uh, simplified forms of what your computer uses to make decisions, and this will allow your devices to respond uh, to more complex conditions. So there's three basic types of logic gates, and, or, and not, with not being the simplest. It's just a torch stuck to a block. A redstone torch, not a normal torch. So here's a simple example. It's just a wire leading to a lamp, and I hit this button, and the lamp turns on. Exactly as you would expect it. This is the same thing, except with part of it replaced by a not gate. The lamp is already on, and hitting the button instead turns it off. This is because whenever the block that the redstone torch is stuck to is getting power, such as right here, the button will power this redstone wire on top. Once this block is getting powered, the torch turns off. So this is what allows the not construction. It's good for more than just inverting signals. It can also move signals. So here I have two little contraptions that do the exact same thing. I press a button on the ground and it lights up a lamp above it. There's that and that. I personally prefer building with the design on the right just by stacking NOT gates on top of each other because that takes up less space, it takes up less redstone, and achieves the exact same effect. This works because even numbers of NOT gates more or less cancel each other out. So here's a NOT gate here, powers this NOT gate, and so this turns it on, this turns it off. So this acts exactly as the first one does. I press the button, the lamp turns on. Button retracts, lamp turns off. You can use odd numbers of them to still get the effect of just using one. So the lamp is on, I press the button, the lamp turns off. And you'll see that there's three NOT gates there. Here's the same example vertically. The lamp was on, I press the button, it turns off. So just remember that even numbers of NOT gates cancel each other out. OR is the next operation. It's easier to build, but a little bit harder to understand. That's because what we think of in English as OR is what we call in the field of discrete math exclusive OR, and the OR that we're using here is what's called logical OR. Exclusive OR would be, I need to get in my car if I need to go to school or I need to go get groceries, but not both. Logical OR says I need to get in my car if I have to go get groceries, or I have to go to school, or I have to do both. So unlike the NOT gate, where you have to have that torch construction, you just need to connect wires together for OR. So here's an example that I was too lazy to get a second or fix a sign for. So if I'm getting power from this daylight sensor or I'm getting it from this button, I want this door to be open. So right now it's getting it from the daylight sensor, and hitting the button has no effect on the door because it's already getting power. However, if I make it night, oops. I swear I know how to type. There we go. It's nighttime. It's no longer receiving power from the daylight sensor, but I can still power it with the button. If you want to be a little bit more mathematical about it, this is what's called the truth table for OR. The T and F are true and false, and the two columns on the left are the inputs, and the column on the right is the output, in this case, the button, the daylight sensor, and the iron door. So if you look at this, the iron door, exactly as we saw, receives power if it's getting power from just the button, just the daylight sensor, or both. For future reference, I may use zeros and ones, if one is true and zero is false. That's just because of my training as a computer programmer, and that's how I think about it. The final logical operation is AND. Here's the truth table for that. You'll see it responds if only if both of the inputs are true. So, here's how you build an AND gate. It is 3 blocks in a row with a redstone torch on each end on top, a redstone wire connecting them, and a torch on the side. So for this example, the lamps will turn on only if the lever has been pulled and the button has been pressed. You see this is an AND gate turned around. So pulling the lever does nothing. Pushing the button does... Oh. The lever is off, pushing the button does nothing. But turning the lever on and pushing the button allows it to respond. I can even cut the power off prematurely by flicking the lever. If I can time it right. Yeah. For those of you that are curious, this is the exact same thing, except with 3 NOT gates and an OR, and they act exactly as an AND. I need to pull that lever and push this button in order to turn it on. This is because of De Morgan's laws. If you are at all interested in learning a little bit of Boolean algebra, you do not need to know Boolean algebra to be good at Redstone. In fact, I rarely use it myself. It does help a lot, though. Not so much in the layout of the circuits, but just understanding what the circuits are doing and what the logical operations mean. It's more just, it lets you think the right way to do it. If you also get really good at it, though, there are 3 more logical operations, exclusive OR, not OR, and not AND, that you get to mess with, too. Those are much less intuitive and harder to explain, so I'm not even going to try here. But anyway, this is the end of my introduction to logic gates. From now on, I'm just going to be showcasing one piece at a time and showing how to use it. So, join me in my next video. Now I'm actually going to show you how to build stuff.